Let's continue our discussion on the electrostatic equilibrium. Suppose a conductor of arbitrary shape contains a cavity as shown in the figure. Assume no charges are inside the cavity. Based on our discussion in last lecture, we know that the electric field in the conducting shell must be zero and the potential on the surfaces of the shell and inside the shell has the same value. Now, let's examine the region inside the cavity. We choose 2 points A and B arbitrarily on the cavity's surface. These 2 points must be at the same potential. We write down this equation to calculate the potential difference between A and B. Because potential difference is zero, the line integral of the electric field must be zero. This is valid for all integration paths taken between any 2 points on the conductor. Therefore, the field E must be zero everywhere in the cavity. We have known that if a solid conductor in electrostatic equilibrium carries a charge, the charge resides on its surface. Now we have a conductor with a cavity and 2 surfaces exist, outer surface and inner surface. In this case, where does the charge reside? Only on the outer surface, or the inner surface, or both? Assuming the charge resides on the inner surface, we choose a surface as our Gaussian surface inside the conducting shell, as drawn by the dashed blue line in the figure. By applying Gauss's law, the flux through this surface is zero, and hence the net charge on the inner surface must be zero. This suggests the magnitude of the positive charges is equivalent to that of the negative charges. We notice that if this assumption is true, the potential difference between any 2 points on the inner surface will probably not be zero. This contradicts the property that the potential is constant on the conductor surface. Therefore, the charge doesn't reside on the inner surface but the outer surface. Then, what if the cavity contains a charge Q? Please look at this figure. A Gaussian surface is chosen inside the conducting shell. By applying Gauss's law, the flux is zero. Since the charge in the cavity is plus Q, the charge of equal magnitude and opposite sign must be induced on the inner surface so that the net charge enclosed by the Gaussian surface is zero. Correspondingly, additional plus Q is also induced on the outer surface because the net charge carried by the conductor must be conserved. Next, let me show you some examples of conductors in electrostatic equilibrium. Please look at this figure. As discussed, the electric field is zero inside the cavity, even if an electric field exists outside the conductor. The charges are distributed only on the outer surface of the conductor. If you are sitting in this hollow conductor now, you are safe because the external field is shared by this hollow conductor. Another case here, if there are charges inside the cavity, the induced charges will reside on the both inner and outer surfaces of the conductor as shown in the figure. But if we connect the conductor to the earth, the positive charges on the outer surface and the electrons from the earth through the wire cancel with each other. In this case, the region outside the conductor is field-free region, even though there are charges inside the cavity. That is, the internal field could be shared by the hollow conductor. We know the magnitude of the electric field just outside the conductor surface is proportional to the surface charge density sigma. A conductor of arbitrary shape is carrying a positive charge as shown in the figure. Notice that the surface charge density is non-uniform. The surface charge density is high where the radius of curvature is small, and low where the radius of curvature is large. Hence, the electric field would be very strong near at sharp points of the conductor. A phenomenon known as coronal discharge is related to this property. When the electric field near the conductor is very strong, free electrons from random ionizations near the conductor move rapidly, which could ionize more molecules, creating more free electrons. When the recombination of these free electrons with the ionized air molecules occurs, the glow can be observed. This ionization process and the coronal discharge are most likely to occur near the sharp points of the conductor with an irregular shape. So far, we have studied the electric properties of a conductor in electrostatic equilibrium. In the next lecture, we'll move on to another kind of materials, dielectrics.